I have two questions rather, for you. This first one is from 2024. Question 4.3. This is for the 7517 AQA spec, and this is paper 2. You will be able to find this online for free if you search that information up. Okay, so this is a continuation from the other two parts to this question. So we're at 4.3, but they're just reminding us that we are in normalized floating point form, 2's complement, with 8 bits for the mantissa, 4 bits for the exponent. In fact, we can see that structure down here. So it says, here's the number that within the system that they're using, 8 bits and 4 bits, you can't represent that entire number. So we just need to get as close as we can get to it. So write the closest possible normalized representation of this number in the box below. It should show you're working. 3 marks, so we need to actually show off what we can do. Also, the going advice is that even if you get the wrong answer, if you show you're working, you might be able to pick up some extra marks. So 12.765625. So let's do the 12 first. So remember, this is in 2's complement. So 1, 2, 4, 8. Well, to get to 12, remembering this is 2 complement, we're going to have to put negative 16 in to open up these as positive values. So we need 0, 1, 1, 0, 0. So that's the 12 done. Now for the fractional part. So we've got, and I'm going to leave some space here so I can write in the representation later, but 7, 6, 5625, 5625. So we've got that. Now I'm going to use the times 2 method, again showing my working as I go. So if we times that by 2, where's my calculator gone? So we're going to times that by 2, so 0.7 65625 times 2 gives us 153125. 125. Okay, so then we need to take the fractional part and multiply it by 2. So 0.53, we drop the 1, we're not interested in the whole part. 125 times 2. So we'll get rid of the whole part and then times the whole thing by 2. So 1.0625, 0.0625. Again, we take the fractional parts of 0.0625 times 2. And what do we get for that? So subtract the 1 off and times it by 2. Oh, 0.0625 times 2 gives us 0.125. So 0.125 times 2. So times that by 2, which will give us 0.25. Times that by 2, and we're going to stop whenever the fractional part gets to 0. So times that by 2 gives us 0.5, and then 0.5 times 2 gives us 1.0. Okay, so fractional part is 0, so we can stop now. So if we read this off top to bottom, 1, 1, 3 zeros and a 1. So 1, 1, 3 zeros and a 1. So that's where our fixed point is. Now they want this in floating point normalized. So we're going to have to move this decimal point across until we get the pattern 0.1. It's a positive value in floating point, needs to be normalized. So if we look, we need to go 1, 2, 3, 4 places to the left. So I'm going to write that out. So 0.1, 1, 0, 0. And the remainder of this, so 1, 1, 3 zeros, and a 1. Now the constraint is we have to fit this into 8 bits. So 1, 2, 3, 4, 5, 6, 7, 8. There's the cutoff there. So if I write this again, 0.11, 0, 0, 1, 1, 0. So there's the 8 bits. Now we need to do the exponent. So what did we do to the decimal place? We moved it 1, 2, 3, 4. So we're going to put this in 4 bits in 2's complement. So there is the value 4 in 2's complement. So this is our final answer using the constraints that they've put on us. So if we move this up a bit, we'll write this in. So 0, 1, 1, 0, 0, 1, 1, 0. Exponent 0, 1, 0, 0. Okay, so there's a follow-up question here saying, what is the smallest number of bits that would need to be added to the mantissa, so to this, so that we could represent the number exactly? Because given what they told us, 8 bits is not enough to cover all of this. So how many did we have to chop off? Well, 3. If we put those 3 back in, when we extracted this number, we would get back exactly this value here. So we chopped off 3. So to get it back to what it was, we need to add in 3 bits, the 3 bits that we chopped off. So the next question was from the 2023 paper 2 7517 paper. It again is just looking at normalized 8-bit, 4-bit exponent 2's complement floating point numbers. So this time we've got a negative number. They're wanting us to show off how we negated this, as well as doing the normalization. So 3 marks again, answer goes down here. So negative 23.25, we start off by representing positive 23.25. So 23, we're going to need 1, 2, 4, 8. So 8 add 4, add 2, add 1 gives us the 20. So that's, what's that? No, we need more. So we need 16, add 4, 20. That'll get us to the 23. Unfortunately, this is in 2's comp, so that we need to add another bit to keep it positive. So 0, 1, 0, 1, so that gives 20, and then the 2 and the 1 will give us 23. So there's the whole part. And so we need to do 0.25, well that's pretty straightforward. So we need 0, 1. So 1 over 4, 0.25. Okay, so there is the representation. It's 1, 2, 3, 4, 5, 6, 7, 8 bits. Next up, we need to negate this because this is positive 23.25. So we find the least significant one, which is this guy here, and we're going to flip the bits to the left of that. So 1, 0, 0, 0, 1, 0, 1. Don't forget the decimal point. Okay, so this is in floating point 2's comp, but we need to float the point so that it reads, the rule is 1.0 for negative numbers for it to be considered normalized. So if we move 1, 2, 3, 4, 5 places to the left. So if we write that out, got 1.0, 1, 0, 0, 0, 1, 1. What did we do to the decimal point? We've moved it 5 places to the left. So to get it back, we have to instruct or put into the exponent the instructions to move it 5 places to the right. So that's positive 5. So if we do 0, 1, 0, 1, so 1, 2, 4, negative 8, 1 and 4 is 5. So final answer is 1.01, 0, 0, 0, 1, 1, and positive 5. If we just check that back, if we move it 5 places, 1, 2, 3, 4, 5, it would go there, and that indeed will lead us back to that. So at this point, I've got the right answer. I've shown negation, so if I just put that in, so negation, okay, so there we've got the fractional part, so 1 over 2, 1 over 4. That's pretty much all of the information I need. Okay,